This is the Chapter 18 whiteboard lecture on relative dating, covering PowerPoint slides 4 through 18. Relative dating in geology involves a set of rules or principles that we use so that we are all interpreting what we see in the same way. That means that we can use other people's information, data, and interpretations when we're looking at our area, and they can use ours when they're looking at their area. The first principle is uniformitarianism. And this just tells us that the geologic processes that we see happening around the surface of the Earth today were the same as those that were happening in the past. So if we see, say, ripples in a rock, preserved ripple marks in a rock, we can assume that those ripple marks were made in the same way that ripples are made today. We don't need to come up with some new process to explain those ripples. The second principle is the principle of original horizontality. What this tells us is that most sedimentary rocks are deposited as layers that are parallel to the surface of the Earth or horizontal. This is true because most sedimentary rocks are actually deposited from bodies of water, and bodies of water are always parallel to the surface. So therefore, those layers are created in a horizontal manner. The reason we need this is because we see many rock layers that are not horizontal. And so this principle tells us that we need a geologic explanation for why the rock layers are not horizontal, because we know they were deposited as horizontal layers. That tells us something has happened to them since. This is a nice example of layers of rock which were deposited horizontally because they are all sedimentary layers. And after that, at some point in their history, the entire sequence of rocks was tilted. The third principle of relative dating is superposition, and this just tells us that younger rock materials are generally deposited on top of older layers. This is very intuitively obvious if you ask somebody to collect your mail while you were on vacation and they came every day. When you returned, you would find that the oldest pieces of mail were on the bottom of the pile and the youngest, most recent, were on the top. So we're saying the same thing about rocks. We can assume that this rock layer down here is older than this rock layer up here because this one is lower in the sequence and this one is higher in the sequence. The fourth principle is lateral continuity. And this just says that in general, sedimentary rock layers will extend horizontally in all directions until one of two things happens. Either they grade into a different type of sediment, which we're seeing over here, which tells us that at this point, geographically, the environment changed. So whereas this rock was being deposited here, the environment was different as you moved this way, and a different rock was being deposited here. Or the second possibility is that they can actually get thinner as you move towards the edge of a basin. So you can see each one of these rock layers is thinning out as it gets closer to a basin. So we can assume that rock layers are extensive horizontally in all directions unless we encounter one of these two things. So that means that if we are over here on the edge of a canyon and we want to know what is going on over here, if we're standing on horizontal sedimentary layers, we can assume that they are the same layers that were over here or will be over here when we eventually get over here to look at them. This happens because basically canyons are cut down by water, so a tiny bit of water there at the bottom. So they don't disturb the type of layers that you get on either side. They simply erode them away. So you can expect these layers to continue laterally, again, horizontally across the canyon. The fifth principle is the principle of cross-cutting relations, and this simply tells us that any feature that cuts across rock layers has to be younger than the rock layers that it cuts across. So we've got a couple of examples here. This is an indication of a fault right along here, and you can see how the layers of rock have been displaced. This used to be continuous with this with this, etc. So this feature, this fault, cuts across pre-existing rock layers. It couldn't have cut them if they weren't already there. So that means that the fault itself has to be younger than the layers it cuts across. We see the same thing here with a basalt dike. So this is an igneous intrusion. So we had these layers here, and then magma rose up through a crack and was deposited inside that crack and eventually crystallized. But it couldn't cut across these rock layers as it does on the edges if those rock layers hadn't already been there. The sixth principle is the principle of inclusions, and this tells us that a piece of rock that's included in another rock must be older than the host rock. So a good example of this is simply a conglomerate, one of the rocks that we learned in the sedimentary rocks. So a conglomerate is made of pebbles, fairly large pebbles, so we can see those here, and then they are enclosed by this matrix which kind of holds them all together. So this is a rock, this pebble, right? That was some rock before it broke off and then got deposited with these other pebbles here and then eventually cemented together. So this pebble must be older than this entire conglomerate rock. So if we see any kind of an inclusion in another rock, we know it's older than the rock it's in. Next, we're going to talk about unconformities, and sometimes these are included as the seventh principle. An unconformity is not a rock layer. Instead, it's a boundary between two rock layers, and that boundary marks where rock layers are missing from the timeline. This is usually the result of erosion, so rock layers were originally deposited, but then the environment changed, erosion happened, and some rock layers were eroded away. We don't know what those rock layers were. This is sort of like having pages of a book you're reading having been torn out. You know pages are missing because you can see that the page numbers jump, but you don't know what was written on those pages. So we recognize three different kinds of unconformities, and these are sort of like our way of saying we go here from page 100 to page 150, so 50 pages are missing. We can recognize three different ways of seeing that something is missing, and we're going to go through each one of those. So the first unconformity is called a non-conformity, and this is a boundary between an unlayered crystalline rock and sedimentary layers on top. So unlayered crystalline rock is basically an igneous or metamorphic rock, with the exception of one layered igneous rock. The layered igneous rock, and the reason the term unlayered has to be in here, is a lava flow. A lava flow is much more like a sedimentary rock because it flows out at the surface of the earth and is therefore a horizontal layer that forms at the surface. But any other igneous or metamorphic rock is a crystalline rock, and these rocks form deep in the earth. So the only way that you could erode off the top of one of them is if it had been exposed at the surface. And that would mean a lot of rock layers must have been eroded away before this crystalline rock could have been at the surface. So what do we see at this boundary? we might see evidence of erosion, and that could be sort of an uneven surface at the unconformity boundary, but it can also include inclusions. So we've got some inclusions here in this particular gray sedimentary rock layer. And remember that the principle of inclusions tells us that the rock that's included must be older than the host rock. So that means that this rock, this green rock, must be the old one compared to this gray rock, which is younger. And the same thing here, right? This inclusion also tells us that the yellow rock must be older. So we can see pieces of this igneous pluton in this sedimentary rock. And that means that at some point, this was actually the surface of the earth, and this rock here was getting eroded, and we created pebbles of it. So that's the kind of thing we might expect to see at a nonconformity, that evidence of erosion. But just the fact that we have crystalline rock here with sedimentary rock right on top of it, right here, is enough to tell us that that must be erosion, because this rock, the crystalline rock, can't be at the surface unless a whole bunch of layers were eroded off of it first. Next, we have an angular unconformity. So this is a boundary where you have tilted sedimentary rocks underneath the boundary and horizontal sedimentary rocks on top of the boundary. So it could look, if this was just a piece of rock here and this was our unconformity, what we would see are tilted sedimentary rocks with horizontal sedimentary rocks on top of it. The important thing is not so much that these layers are horizontal, it's that they're not parallel to the layers below them. So if you had a block like this with an unconformity like this, and you had layers that were like this, and then layers that were like this, we would not call that angular unconformity because these layers are parallel to these layers. It has to be where the layers are not parallel to each other. So over here on the right-hand side, we have a figure which just shows how this can develop. So we start out here at 1 with a deposition of horizontal layers. And then something happens, and those layers get lifted up, and they make this nice fold here. Now, to have an unconformity, we have to have some sort of erosion, and that's what we're seeing in the next step. Basically, this hill has gotten eroded off, right? All of this goes away, and that's what we're seeing here, this new surface. And we can see that erosion surface right here. It's a little wavy, not terribly flat because of the erosion process. Then the environment changes again, and we begin to get sedimentary layers deposited on top of that erosion surface. And that gives us this angular unconformity between these layers that are tilted and these layers that are not parallel to those. Here are a couple of examples of unconformities. So we have sedimentary layers here and sedimentary layers here. And notice neither of them are horizontal, but they are also not parallel to each other. And that's what means we have an angular unconformity. Then we have one down here where we have actual folds. And at some point, they were exposed and eroded, and these horizontal layers were deposited on top of them. Finally, we have a disconformity. So this one is the hardest one to see in the rock record. It's the one where maybe you don't have page numbers in your book, and so you're not positive. You have to look for other information to tell you that there's a missing layer or more than one missing layer. This is because in this case we have sedimentary layers below and above the unconformity. So in this diagram, the unconformity again is this dark wavy black line. And we have a sandstone down here that's horizontal, and we have a limestone up here that's horizontal. So how do we know that there is actually missing time here? One thing we can look for is that evidence of erosion, that uneven line that is the contact between one layer and the next layer. Another way is to look for fossils. Sometimes you will find fossils in one of the layers that are much, much older, millions of years older than fossils that are in the layer directly on top of it. And the best explanation for that, for all those missing years of fossil life, is that those layers that had those fossils in it have been eroded.